start. So this is the example in which we studied before the mixture, right? So although this was with respect to the Hopf bifurcation and we learned many things about, but today we are going to learn one last thing about the equilibrium points, which is the structural stability of the equilibrium points of the orbits. Okay, what does it mean? Now, by the word stability, that everybody knows, that is what we mean by a stability of a system. But now it is about the structural stability of an equilibrium point. What does it mean? That means we have studied different equilibrium points, right? Stable node, stable focus, unstable focus, and then saddle point, like center case. Now, if somebody asks, that is for a nonlinear system, specifically where you have a variable parameter, then that is how long will that one particular equilibrium point or the nature of the equilibrium point will continue to remain the same. That is called the structural stability. Have you understood? That means, suppose that one of the equilibrium point exhibits the center case. Okay. Now, with the parameter variation, suppose they are mu, alpha, or beta, whatever, even under the parameter variations, suppose for a small change in the parameter, will that center case like survive? That is the question. Like here, when you have mu, so that's why there is maybe at whatever I just said, it is not exactly clear to you. So it is like better to discuss with this example. So this is the example which we took before the mixture, right? Now that is what was the equilibrium point 0, 0. Then what was the Jacobian? This must be the Jacobian mu minus 1 plus 1 mu, right? Now what are the eigenvalues of the Jacobian matrix? So this is of course like J with respect to 0, 0. Sorry. Now here is the mu, that is at this moment we don't know, that is what is the value of mu, like let's see. So like this is the case, right? So this is the eigenvalue. Why don't you sit here? I hope all of you remember this one. That is the eigenvalue. It was mu plus minus j1. Like very simple, from this matrix only we can find this expression. Now what happens if mu is greater than 0? It will be unstable focus, right? What happens if mu less than 0? It is a stable focus. Now let's say that is mu greater than 0. It gives you an unstable focus. Fine. Whether the value is 0.1 or 0.1 or 0.5 or 1, 2, 5, 10 or even 100, it will always remain as unstable focus, right? The same for mu less than 0, it gives you stable focus. Right? Now whatever may be the values, minus 0.1, minus 0.5 or minus 1 or minus 2, minus 5, minus 10, so on and so forth, the stable focus will remain as it is, right? So if there is some perturbation, like what we wanted to be, like suppose x dot equals to ax, that is for our LTI system. If there is a perturbation, suppose x dot equals to a plus delta a into x, it is the perturbed LTI system. And in practice, you know that is always there is a chance of some perturbation which comes due to uncertainty or some other factors. Now that represents this mu here. Suppose there is a perturbation, and with that there might be change in the mu value. Okay. So, but as long as this stable focus here, unstable focus, or even stable node, unstable node. Usually for the node cases, whenever there is this kind of like parameter, no, node cases can also count in case of the parameters, right? We have seen in the first two type of bifurcation. What was that? Transcritical, and the other one, the first one, saddle node, right? So you see for those kind of cases, for stable focus, unstable focus, stable node, unstable node, even saddle point. For all of them, the nature will keep continuing for under small perturbation of the system, which like tends or which imposes some changes in the parameter. But what about the center case? Mu equals to 0. That gives you the center case. Right? Now, if this mu like changes slightly, say for example, if this is plus minus 0.5 or suppose if it is plus minus 0.1, it is a very small perturbation, but still that is sufficient enough to kill the sustained oscillation, right? Are you getting? The center case will occur only when mu is perfectly zero. But suppose there is some perturbation on the system, like which forces the mu to take some little bit of non-zero value, whether in the plus side, whether in the minus side. So immediately the center case will turn into either a stable focus or an unstable focus. If it is plus, it will become an unstable focus. If it is minus, then stable focus, right? So this is about the stability of equilibrium, not equilibrium point. This is about the stability, structural stability of equilibrium point. That means this kind of structures, like the stable or unstable focus or even the saddle points, they can sustain under small perturbation. So they are called structurally stable. Whereas only the center case you see, this is very susceptible to noise or any change in the system. So this is not structurally stable. This is the situation about. Are you now getting? Just try to think about the situation. Like mu is a parameter that is which may change. Like suppose originally there was a value of mu that can change depending upon a parameter. Depending upon some perturbation in the system.
Without the perturbation, the system should be
If the mu value remain constant, suppose that mu equals to 0. Ideally mu should be 0. Suppose under some case, then it must give you the sustained oscillation in the center case. But suppose due to some physical perturbation on the system, which can make some changes in the value of mu, then if the mu takes on some non-zero value, then what will happen? Immediately the center case is gone. That's why the center case is called not structurally stable, whereas the others, they are called structurally stable. Okay? That is whether the nature of the equilibrium points, whether that sustains or not. That is our question. So that's why it is called the structural stability of the equilibrium point. That means whether the nature of the equilibrium points remains the same under little perturbation. That is the meaning of structural stability. Is that clear for all of you? Just take your time and think about it. If you have any question, please ask. Not only for this example, you consider the Van der Waal example, the same thing will happen. In the Van der Waal, that is the example of where the nonlinear damping, right? There also we have that parameter epsilon or mu. If you make that mu equals to 0, it turns into a pure linear harmonic oscillator, right? But if that parameter mu is there, then it is not a linear oscillator. Then it is a Van der Waal oscillator, a non-linear oscillator. And what are the differences between a linear harmonic oscillator and a non-linear oscillator? What are the points we learned? Tell me one by one.
damping changes with displacement.
Sorry?
Damping depends upon displacement.
Initial condition. Right? Please check your notes. What are the points we learned? You should not forget it so fast. We discussed actually 3 points, like 3 differences between linear and non-linear oscillation, right? Linear oscillation means it is just like an AC oscillator circuit, a linear harmonic oscillator, and the non-linear oscillation means it's a limit cycle, right? The very first difference is that the non-linear oscillation, the amplitude of a non-linear oscillation doesn't depend on the initial condition, but in case of linear, it depends upon the initial condition, right? Then, what is the second point? This non-linear oscillation, so that limit cycle, it is an isolated periodic orbit, right? But in case of linear, if you change the x0 even by 0.1%, you will be getting another closed curve. So this is a family of all closed curve. They are not isolated. But for nonlinear oscillation, you will get a non-trivial solution in the sense it will give you a particular isolated closed curve, right? That is another difference. Anything else? Third one is the structural stability. The limit cycle, you see, that is depending upon the mu value. Even if there is some change in the mu value, whether in the positive side or negative side, the limit cycle will be there, right? Because it doesn't depend upon a particular value of mu or initial condition. But if it is a center case, then immediately the mu value takes some non-zero value, then this sustained oscillation is stable, right? That is the third point. Take some time to think about the situation, see the Van der Pol oscillator once again and ask me if you have any questions.
Can you explain the part of the limit cycle?
Limit cycle, the third point. So what are the differences we learn? First of all, all of you, this time like repeating once more. What is the first point between the linear and non-linear oscillation? The dependence upon initial condition, right? What was the second point?
The accelerated closed curve will be
third point, or if you asked about the third point, structurally stable or not. Say for example, once again we go back to the this example or Van der Pol oscillator, the Jacobian at 0, 0, you will find mu minus 1 plus 1 mu, right? When it would be a center case, if this is if mu equals to 0 perfectly, then it's a center case, right? But what happens if mu not equals to 0? Center case is gone. That's why the linear oscillation, that is structurally unstable. Okay, that is the difference. So please don't get confused about the stability of equilibrium point and structural stability. Okay, so the structural stability is the new thing today what we have learned. So once again, structural stability means whether a particular nature or whether a particular nature of an equilibrium point, whether that sustains under some perturbation. That is the structural stability. Okay. So here mu is a parameter. It can have a fixed value which we don't know, but the case becomes different when there is some external disturbance or some perturbation. Suppose there is x plus delta x, or even fx plus some perturbation, which can make some changes in this mu value, which is unknown to us. Now that can lead to this kind of reference. Okay? Doesn't make any changes if it is an unstable focus or stable focus. That's what I say. Suppose if mu is already positive, whether that is some more positive or some less positive, that doesn't matter. Suppose it was already mu was 1. And then due to the perturbation, it becomes 1.5 or 2, or maybe it becomes 0.5 or 0.2, 0.1. But as long as it remains positive, the unstable focus property will continue, right? The same thing for the other one. Suppose it is already minus 1. Due to some perturbation, it can become minus 1.2 or minus 1.5 or maybe minus 0.8 or minus 0.5. But still it will remain in the negative zone, so the nature's stable focus will continue. So that means the stable focus or unstable focus, this nature is structurally stable under perturbation. Is it now clear? তোমাকে দেখে অন্য প্রশ্ন মনে হচ্ছে? Is it fine? Now, if you remember, before the mixer I also mentioned that is linearization technique, right? Analyzing the stability of equilibrium points by Jacobi linearization. It helps us a lot because it is easy to perform and easy to understand as well. But sometimes it may not be effective when it fails. That is, if the Jacobian has zero eigenvalue or complex conjugate eigenvalue with zero real value, right? So in this case, I think I already said that is, suppose in this case, if it was only, like supposing that for mu equals to, if mu equals to 0, then what will happen? The linearization technique will give you a center case, right? Not mu equals to 0. I think for mu equals to 0, it will give you the center case, right? But what happens, that is ultimately, that is when we check about the stability, then when you have the 0, 0, then from that we cannot at all understand that there is a stability of the limit cycle, right? So that is one of the problems. That is, for this case, the Jacobian, I think this is the Jacobian for the 0, 0, and you will remember that point, like from this, when you are finding the equilibrium point, and then you are finding the Jacobian, and then from that, you see that is either we see that it will be an unstable focus or a stable focus, or for mu equals to 0, it's a center case. But originally, that is, unless and until you convert that into the polar coordinate, we don't know that there is a possibility of limit cycle. And in fact, in this case, there will be a limit cycle. If you remember, that is, after the polar coordinate, what did we, I think that is, we got r dot equals to mu r into 1 minus r square, right? And theta dot equals to 1. This we got, right? So if you don't do it, then we don't at all know what we can't at all find that there is a possibility of limit cycle, or in fact it will give you a limit cycle. Okay? So this is one of the case where exactly from the linearization technique, that is, we may not be able to understand that is what is the exact phenomenon. Another example, suppose you have x dot equals to ax cube. Okay, x0 belongs to r. First you analyze the stability of this system by linearization method. What will happen? This is suppose f of x. So what is your del f del x? Right? Here what is the equilibrium point? Of course, the 0 x star equals to 0 is the equilibrium point. So what about del x at x star equals to 0? It is 0. Right? But what this is 0, right? So x dot equals to 0 means it is a like marginally stable system. But when you decide, or when you conclude that it's a marginally stable system, then originally it had a parameter a. A can be greater than 0, a can be less than 0. But here, if you would like to compute the stability through the linearization method, it is irrespective of the values of a. So that's why in some cases it may be misleading. It matches only when a equals to 0, because a equals to 0 gives the original system x dot equals to 0. So only for a equals to 0, these two results will match. Okay. Now for the other case, a greater than 0. What will happen? X dot equals to ax cube. You apply the stability criteria. for like scalar systems, what did we learn? That is x into x dot. If that is less than 0, then asymptotically stable, converging, it will converge to the equilibrium point. If x into x dot greater than 0, then it will diverge, right? Here what happens for A positive? Unstable. Why unstable? Because x into x dot that is greater than 0, right? For all is greater than 0, isn't it? And x into x dot is less than 0 for all is less than 0, isn't it? Sorry, which one? It will also be greater than 0. Right? Please check whether I am getting mistake. Whether that is x is positive or negative, x into x dot will always become positive, right? So if x is originally in the positive direction, it will keep on increasing in the positive direction. If it is originally in the negative direction, it will keep on increasing in the negative direction, right? Unstable. Now what happens if A less than 0? So x dot basically, then what will happen? This is it is like that. For A less than 0, just for a numerical example, I have considered A equals to minus 1. Then it becomes x dot equals to minus 16. It's asymptotically stable, right? Can you now, that is, do you understand? That is why the linearization technique, it fails or leads to some ambiguous result, especially when it has a 0 eigenvalue or eigenvalue with 0 real part. You see, then that is, it matches only when the originally A equals to 0. But if A is non-zero, in the positive case, it is completely unstable, not marginally stable. And in the negative case, it is asymptotically stable, but never it is marginally stable, right? But if you go by the linearization approach, irrespective of the values of A, it will always give you that it's a marginally stable system. That is the idea. So in this case, the linearization technique, from the linearization technique, we cannot understand or we cannot find the existence of the Levy cycle, right? So that is one of the big points. Like here we are, whatever we are getting, only about one equilibrium point, which is the origin, and whether the origin is stable focus or unstable focus. But a phenomenon like limit cycle, which is very important in the case of nonlinear oscillation, that is impossible to find from the linearization approach, right? So this is one case, and in other case it is purely about an ambiguous result about the stability. So please remember these two cases. So similar other cases may happen. So although what is the takeaway point? Then although the Jacobi linearization approach is really handy because it is easy to understand as well as easy to apply, but in some cases it may lead to ambiguous result. Okay. You can answer this, sir, why you are discussing all these points. The reason is that we need something, really, what should I say? That is, we need a systematic approach for a clear-cut analysis technique by which we can understand the stability of a nonlinear system without any ambiguity, right? Once again, that is for this linearization approach. What did I say? That is this linearization approach, although that is it is quite easy to apply and easy to understand, but in some cases it may confuse us or it may lead to ambiguous results. So that urges that is we must have a systematic stability analysis tool, especially for nonlinear systems, right? That's what the Lyapunov comes into. The Lyapunov stability analysis technique, that is a systematic and well formulated approach by which we can analyze the stability of both linear as well as nonlinear systems without any ambiguity, right? There is only one difficulty, that the choice of the v function, which is not unique, and also although there are some guidelines for choosing the v, but no one can guarantee that is like we can find the best v for a system. That is the only problem. Okay, so Lyapunov stability analysis, that is a very powerful approach, especially for the nonlinear systems, but with only one difficulty: how to construct the v function or the energy function. Okay. I think at the beginning of the course we discussed about the stability concept, right? The ball concept and then asymptotic stability, continuous stability. So there is the stability in the sense of Lyapunov. Okay, so let us write down the definition. How should I start, Birman? How should I start? That is, we know that what is like stability in the sense of Lyapunov, but if we need to write it technically, how should we approach? Do you remember once I said that is, if you have to write a definition, lemma or a theorem, the actual result part will come at the end. First you have to start with all the suppositions or the assumptions, okay? Then if you have to define something, finally the proper statement or the actual result will come. So here when you have a nonlinear differential equation x dot equals to f of x, it need not be scalar, it can be vector as well. So first of all there must be an equilibrium point, and even before that it should have a solution, right? So and then for a nonlinear system, if somebody asks you that is okay, what is the condition under which you can guarantee that fx will have a solution? That means this differential equation will have a solution, I mean existence. So for that is the minimum, like the restriction which needs to be imposed is that fx must be locally Lipschitz. We will discuss more about the Lipschitz condition. As of now I am just mentioning that. I think you can understand that is I cannot certainly write that it is about the entire domain Rn, right? Because that is the main problem with the nonlinear system. The stability which we analyze that is mostly local in the sense. You have already seen in case of simple pendulum. That is for a zone, it is either a stable focus or some other zone, it's a saddle point, right? So that's why whenever you write something for nonlinear system, you should never write for the whole array. Always there is a domain D, that is it is comes from the local cells, okay? So let fx be a locally Lipschitz function over a domain D that includes the equilibrium point f of x star 0 equals to 0. That includes the equilibrium point x star equals to 0. That is f of 0 equals to 0. And to be technically correct, here we should write in this case. Why? Because if there are multiple, then after that what I am going to write, that will lead to an ambiguity. It will be clear. So now you please read out the whole thing. This is called, so once again, whenever you write a definition or a lemma or a theorem, then it always starts with the supposition. That means the description of the problem. Here, the description of the system. After that will come, that is if you have some further definition or a variable, something that you need to write, okay? And then finally we will write the actual result, okay? But if this is a definition, not that complex. Later, after that, when I will write the Lyapunov stability theorem, then you will find that is okay. There are actually three steps for writing a theorem, which is very essential for understand, for especially for the MTech and the PhD students, those who are going to write a thesis or a report or a paper. For them, this technical writing, this is very much important. When you write a paper, if you can't write it in a technical format, it will be desk rejected. So that's why, like for those who are like planning paper, usually for the PhD students, for them it is essential, that is how to write the mathematical results. Okay, that's why that is in all of my classes, I keep on saying the same thing so that you know how to write.
So why do you write the equilibrium point to be external? Can you not apply the other equilibrium?
Why not? That is, if there is another equilibrium point, then only that is you have to shift that. That means suppose x star not equals to 0. Then you bring in another variable. Suppose x star not equals to 0. Okay. In that case, you have to change the variable. Then that is y is defined to be x minus x star.
So we will have to change the whole system.
Why do you do that? Because if for your system, if 0 is the equilibrium point, that gives us a lot of advantage, not advantage, actually a lot of convenience in the theoretical calculations. That is the only reason, nothing else. If you have a non-zero equilibrium point, simply that is we apply a change of variable. Then after that, that is finally we have to find out the x dot or here the y dot. Then from that, what will be your y dot? Y dot equals to x dot minus dot of x dot equals to 0, right? So then that is y dot equals to x dot, that is equals to x dot minus 0 means x dot. So x dot means f of x, but now we have to express it in terms of y. So that is f of y plus x star. That is the situation. Please check the first page or the beginning of chapter 3 of Khalil's new book. For this one, those who have confusion regarding that, please check the first 2 pages of chapter 3 from Khalil's new book. New book means whose full soft copy I shared at the beginning. That means nonlinear control, the global edition. Okay. First 2 pages of chapter 3 of Khalid's new book. Old book means whose scan copy Moinak uploaded, that is nonlinear systems, but this one nonlinear control. Okay, the global edition. Okay, then the supposition part is over. Now I have to write the definition of the stability. Okay. Then equilibrium point, in short I am writing, but you should write it in full. Then the equilibrium point, x stat equals to 0 is said to be stable in the sense of Lyapunov. Can anyone tell me when, that is, we explained that delta and epsilon concept, the delta was radius of the ball for the initial condition and epsilon was for the ball covering the entire xt. So which one depends on who? Delta depends on epsilon, right? The other way. Once again, you remember that is, if you have to keep the entire trajectory within a 10 centimeter radius ball, then accordingly you have to decide that is what would be the inner ball, that is within which you have to keep the initial condition, right?
That means that epsilon
The other way around. That's what I said. Then suppose you wish to, that is, keep the entire xt, entire trajectory within a ball of 10 centimeter radius. For that, you will have to find out the radius of the inner ball within which the initial condition must be there. It is not the other way. If for each epsilon greater than 0, there exists a delta greater than 0 such that norm of xt0, that means initial condition, less than delta implies norm of xt less than epsilon for all t greater than equals to t0. That is escaping in the sense of Lyapunov. Okay. You now read out the whole thing and see whether you are confused or not. I'm about to write the second one, which is asymptotic stability. This is just stable, right? After that, the special case will come, asymptotic stability. But first, you tell me whether you are fine with this or not. Check word by word whether you can understand. Why I am writing the entire thing? Because after that, ultimately you will be studying from the book, right? So there, that is, if you now are confident or if you are fine with all the writing, then you won't face any trouble while reading from the book. Otherwise, many times I say that is understanding nonlinear control from a book. Sometimes it is difficult because in the book you will find they write mostly in mathematical terms. That's why there is I am spending so much of time writing all the things on the board so that you find it convenient and comfortable. By analyzing seen this. Can anybody tell me it is for the asymptotic stability? How should I write? Please try.
It's t tends to 0.
But as a full sentence. That is the point. So that is, you see, for the technical writing is that in the mind we can understand that is okay. The asymptotic stability means now that is there will be some delta for which the extreme will go to the origin. In our mind we can understand. But if somebody asks you, okay, you write that in a mathematical, in a technical format, how would you write?
So limit x to t tends to 0.
Again, that's a mathematical condition. What will be the full sentence? That is required for us to learn. See, this entire thing, that is how did I write? That is, first of all, you have to understand it well, then only you can write without looking into the book. For me, that is, I have been like teaching, or that is, I have read the book many times, but you can, it is not by marking up. It is simply that is whenever you are writing something, that is, first of all, you have to understand that thing pretty well. Then you can write from your brain. Otherwise, you will find that is, once you close down the book, then that is, you will hesitate to write. Right? How should we start? The equilibrium point, x equals to 0, is asymptotic. In short, I am writing a dot s dot, asymptotically stable in the sense of the above. Delta greater than 0, x t0 less than delta implies either in terms of norm or simply in terms of extreme. See, it can be written in these two ways, but with the second one, sometimes it can lead to some confusion. Why? First of all, you read out the statement and tell me whether you are fine with this. The equilibrium point, x star equals to 0, is said to be asymptotically stable in the sense of Lyapunov. If for a delta greater than 0, you see, please try to understand. If for a delta greater than 0, now that value of delta for a system you have to decide the delta, right? Again, that is here in the sense of this is asymptotically stable. Here I missed one thing. Can anybody tell me which I missed? Local. How did it strike my mind? The moment I was about to tell for a delta, now suppose that delta it can be 1 centimeter, maybe it is 2, it is 5. How you are going to decide? Based upon your system dynamics, right? And with respect to the equilibrium point. In that sense, it is always local. If I don't write here local, then immediately the confusion will arise, that is asymptotically stable over whole Rn. Although at the beginning I wrote that is Lipschitz function over a domain D. Although it is written, but still for a beginner, if I don't write it, then it may lead to it may confuse us. That is whether it is local or global. But please remember, even if I don't write it local, in the Khalil's book they didn't write it local. Okay, why? Because at the supposition part it is already written the domain D belongs. That is, it is locally Lipschitz over the domain D. Okay, that's why here they didn't write local. But here in my version, I am writing local. That is, I am emphasizing on it so that you don't miss that out. Okay. So here, yes, both asymptotic stability and the just stability, both are local over this domain D. Okay, please be confident about that.
If for a very small data, then we don't know that
No, that how small that we don't know, right? Given a system, for that you have to decide the value of delta. So when you write as a general statement, I cannot write for a small. That small case comes for that when there is delta epsilon both, or even in that case we don't write small, because like maybe you want to keep the entire xt within 5 centimeter radius ball, someone else might want to keep it within a 10 centimeter radius ball. So the delta would be chosen depending upon that epsilon. Are you getting what I am saying? Like suppose someone wants to keep the entire xt within a 5 centimeter radius ball. For that, maybe delta is required 1 centimeter if it is 5 centimeter. Now suppose I want to keep it within a 10 centimeter radius ball. So I am like increasing the freedom. Then I can easily increase the delta. So that's why this delta depends upon epsilon, not the other way around. Okay. And if you think in the exactly in the other way, then it will be more convincing. Once again for all of you, like suppose that is if I wish to keep the entire xt within a 10 centimeter radius ball, my initial condition should not go beyond 1 centimeter ball. Okay. Now you want to that is keep it within a 5 centimeter radius ball. Can you still keep your delta 1? You have to reduce the delta, right? That is the dependence upon epsilon. Okay. You think about the matter and you write in your own words. In the robust class we did that, right?
Locally, asymptotic stability we cannot
Within the D. Huh.
we cannot go beyond that only. That's why
Exactly. Let me give you an example. Again, go back to the case of simple pendulum. Now for that x1, what is x1? x1 is the theta. So if your region is in between minus pi to plus pi, then it will always, it is expected that is it will come back to the 0 point. So that minus pi to plus pi and even that entire vertical strip, that is the D. Okay? Don't worry, it is after learning the Lyapunov, you will solve many examples. From that, it will be clear. Even we have to learn how to find the region of attraction. That too we will learn. Now here, that is, you may have a doubt, that is what does it mean? That is, or whether it is related to this. I hope those who are not there in the robust control class, in robust control we discuss a lot about the norms. In non-linear class I didn't get a chance to discuss, but I only want to add here one point, that is from this, what does it mean? That is the norm of x, it tends to 0 as t tends to infinity. What does it mean? That is, if the norm of a vector goes to 0, then each component will also go to 0. That comes from the norm definition itself. This is one of the property of the norms. That is, if the norm of a vector is 0, it is if and only if the vector itself is 0. Now, what does that mean? There you may have a condition, that is what x equals to 0. What does that mean? So x means actually this is x1, x2 up to xn. When you write x equals to 0, that is each of the component is individually equals to 0. That is the meaning. Okay. So in that sense, this statement is also correct. But somewhat for the beginners, this can lead to a little ambiguity or the confusion, because if you write a scalar signal goes to 0, we understand very well. But if I write a vector goes to 0 at t tends to infinity, you may have some doubt, what does that mean? But this means this one. So please try to understand both of them are equivalent, okay? But how they are equivalent in terms of notation, that I have explained. Before this we learn the Lyapunov stability theorem. First you have to understand that what is the concept of Lyapunov stability analysis. I believe that I discussed that in a nutshell. Can anybody tell me that what is this V function? Why do we need a V function, and what is the concept of stability? Yes. So the Lyapunov stability analysis means this is what we have learned. This is the definition of this stability in the sense of Lyapunov. Now what we are going to do, that is Lyapunov stability theorem or Lyapunov stability analysis. Somewhat these two terms are like quite similar, but please don't get confused. This one is stability in the sense of Lyapunov. That is definition of stability in the sense of Lyapunov. Now what we are going to learn, that is Lyapunov stability analysis or Lyapunov stability theorem. Okay, that is quite funny, but two different things. Are you getting which is for what have you understood?
Since stability in the sense of Lyapunov, and that will be stability of the system.
Lyapunov stability theorem. One is stability definition. Okay. In the sense of Lyapunov. Another one is Lyapunov stability theorem. The second one is nothing but stability analysis tool. This is not a stability analysis tool. This is just the definition of stability. And this one is a stability analysis tool where we need a V function, which is called an energy-like function. Okay. I'm just trying to explain in a very simple way. they always write a V of x equals to x transpose px. I believe all of you have seen, whether you have understood it or not, but I hope that expression is like very famous. That is V of x equals to x transpose px. What does it mean? Or why do we prefer this form?
What is the inverse of the complementary? So from the energy required to take from x0 to x.
That is fine, but at this moment, if I relate with controllability Damian, it will be much difficult to understand, right? Just we try to think from the concept of physics. Suppose you have a physical system, and then what about the stability? If somebody asks you that is what is in physical sense, what is stability? How would you explain? You give a jerk or a perturbation to your system. If it comes back to the original position, then it is stable, or rather asymptotically stable, right? If suppose once the perturbation is withdrawn, that means stability is if a system, suppose if a perturbed system comes back to the original position after the perturbation is withdrawn, then it is asymptotically stable, right? Or if it never comes, if it continuously keeps on going away from the equilibrium point or the initial point, then it is unstable. Or if it goes slightly beyond or slightly away from the point and stays there, then it is marginally stable, right? Now, what happens? That is how you can relate stability with energy.
The energy of the system dies down with time, it's stable.
If the internal energy of the system dies down with respect to time, then gradually it will lose the food to go further, right? That is the same thing for human being. Suppose if you don't eat for 3 days continuously, then you don't have any power or the capacity to work, right? The same thing for while you are working. No, it doesn't apply to me because I get more energy when I don't eat. But for me it is exactly different, so that's why I don't take lunch. If I eat, then I feel sleepy, then that is I cannot work. So during my work time, I generally don't eat. Anyways, for the physical system, if somewhat you see there is this internal energy is decaying, that means we are safe. Finally, that is if the energy is continuously decreasing, ultimately suppose if it represents the energy and decreasing means the V dot x would be less than 0. That means the energy is decreasing. How long it can decrease? Until it becomes 0. And energy 0 means x0, equilibrium. Do you agree? All of you? That is the concept of stability in the energy sense. I will repeat, don't worry, try to understand. Vx is the energy function, right? We generally say energy-like function, but for some of the systems, it can be truly an energy function. Say, for example, you have a RLC circuit. Now, for a RLC circuit, what is the net energy? V of x is equals to half A IRMS square plus half C DC square, right? Now, suppose I just am doing a demonstration about this function, that is how does it come. Let's say x1, that is I, and x2, that is VC. Then can I express it like this? Can we write it? Please check. That is one of the motivating example. That is this x transpose px. So this is my x transpose. This is p equals to p transpose. You can see this is a positive definite matrix, and this is your x. So that's why x transpose px. But this is a very favorable form. Why? Because the off-diagonal elements are 0. But they are not necessarily that the off-diagonal terms will always remain 0. Okay? The only thing is that when you choose an energy function or an energy-like function, you must choose the P to be positive definite. Why? Because energy cannot be 0 or negative. Energy will 0 if the system stays at the equilibrium point, which is called the point of minimum energy. Okay? Once again, that is this P, usually we choose the P equals to P transpose greater than 0. Okay? That is our usual choice. Why? Because this is, finally it will become a positive definite function. Like here, Ex, what now? Okay, there is, I'm coming to that. What I was about to tell you, that is what are the properties of an energy-like function. Okay, there are 3 properties. I'm coming to that. Before that, tell me that is, if you are fine with this. So this is one of the motivating example. That is why that this structure X transpose Px is so famous and so common. And I also said that is this Px, it is called an energy-like function, but for some class of system, for example for electrical systems or for mechanical systems, the V function can even resemble exactly the energy function. Why? I already shown you the example for a RLC circuit for electrical cases. If you take a machine, there also you can calculate the energy. If you take a spin mass damper system, there also the potential energy half kx square, and then the energy for the M, that will be half mv square, right? So in those cases, the V function will exactly resemble the internal energy. But suppose when we learn it in an abstract sense, you have x dot equals to f of x, or suppose you have x dot equals to ax plus bu. You don't know what exactly the underlying system is. Only you are dealing about a class of system. For them, we cannot guarantee that is the V will give you exactly internal energy. That's why we don't write it that it's an energy function. Rather, we write energy-like function. Are you getting? When we do the when we analyze or when we apply the Lyapunov stability concept for a class of system given by x dot equals to f of x, or suppose x dot equals to ax plus bu, where you don't know that what that exactly the system is, then you certainly cannot comment whether Vx resembles the exact energy of the system. That's why if you write or if you mention Vx to be an energy function, it would be misleading. So the generic term is energy-like function, okay? And even a better term is Lyapunov candidate functions. Now there are 3 properties for a Vx to qualify as a Lyapunov candidate function. What did I say? There are 3 properties for a V function to qualify as a Lyapunov candidate. Not all V functions qualify as Lyapunov candidate, okay? of x0 should be 0. That means at the point of minimum energy or at the equilibrium point, the energy must be 0. So it says that is the equilibrium point is the point of minimum energy and minimum energy is 0. Okay? Second one. Vx must be positive definite. That means Vx should be always be positive for, should I stop here or I should write something? For all x belonging to Rn also, x should not be identically equals to 0 because then it will create an ambiguity. That is, it will remain positive definite for all non-zero x, right? And here I should write something in bracket. All these things you see, the thinking should logically come one after one. Here, what should I write?
First differentials exist.
Not only first differential, like here I wrote v dot. That means the v dot here is not about only first partial derivative. I should write that is the first, like v dot must exist and be continuous, right? As in v dot x exists and is continuous. V dot x. Ultimately it will become scalar. But now, yes, an important point. What is actually v dot of x? What is actually v dot of x? That we must learn, right? This is total derivative of Vx, right? Derivative dx, that is also sometimes tried in discussion. This is your because originally you have x dot equals f of x. Now what does it mean? That is f1 of x, f2 of x, ultimately fn of x. Here also in the left hand side it will be x1 dot, x2 dot up to xn dot. That's why I wrote. And this gradient it is always written in a row vector format. Please remember, when we write x, x dot, all of them are written in the column vector format, right? But gradient, del v, that is always written in a row format. And finally, it gives you a scalar term because it is ultimately the rate of change of energy. No, generally that is this del v del x. That is this. It will be generally written as a column vector. To make it as a row vector, I had used the transpose. But if you write del v del x as a row, then you don't have to put it as transpose over there. All of you, please remember that is this del v del x. If you decide to write as a row vector, you don't have to use this transpose. Okay? But if you write it as a column vector, in some of the papers I have seen they use the transpose, but anyways, in Khalil's book or in Slotted book, they don't write a transpose. Then you must keep this transpose. Please remember only one thing, that it must be a row vector, because otherwise this one is a column vector, so this must be a row vector, right? Otherwise you cannot find out that inner product. It is like an inner product. Now, for API systems, this the V function in X transpose Px is quite famous. Okay. For nonlinear systems, we will discuss. We will see many examples where only X transpose Px doesn't work. But for linear system, this is also like quite like well-defined choice and a good one as well. Can you find out that what would be the V dot of X? Please find. If Vx equals to X transpose Px, what will be your V dot of X? Please do it. Like finally, we are going to learn something. इधर ही तो मैं स्ट्रिक्टली नहीं लिख सकता क्योंकि ऑलवेज एसिम्प्टोटिकली स्टेबल नहीं होगा। एसिम्प्टोटिकली स्टेबल का तब चलेगा, ये तो मैं जनरल प्रॉपर्टीज ली। You can also go. I'm just about to end. Okay, just a few minutes. You can go if you wish. And then that is we have to replace V of X equals to X transpose Px, and what is your system? We are doing it for the time being API system. So X dot equals to Ax, okay, and X0 belongs to R. Unforced system. Please remember the stability analysis is for unforced systems, okay? Now V dot of X dot transpose Px plus X transpose Px dot, right? Now X dot means Ax, so Ax whole transpose, so X transpose A transpose Px plus X transpose Pax, isn't it? Take on X transpose, then I'm just slightly rearranging the terms. Right? Now, for asymptotically stable systems, V dot X must be strictly less than 0. For asymptotically stable systems, V dot of X must be negative, strictly negative, right? Doesn't it imply that this one must be a negative definite function? All of you, please look at the board. For asymptotically stable system, the rate of change of energy must be strictly negative. V dot X must be negative. Now, this is nothing but the V dot of X. Now, this is a vector. Now, as a whole, that's it would be like when we discuss about suppose X transpose Mx or X transpose Px, whether it is positive definite or negative definite, how would you say? Depending upon the definiteness of the P matrix. Now here, as a whole, it is Pa plus A transpose P. If this is negative, then it would guarantee that V dot X is a negative definite function. Coming to that. And now suppose in the other way around, if this is negative definite, it will imply that it is strictly negative. This is Lyapunov stability result for API systems. That is, given an API, unforced API system, X dot equals to Ax, if you can find out a P matrix which is positive definite, like figures below, and here generally that is we consider that is P is positive definite, right? So the condition is that I'm just stating the theorem, not writing, because today we are going to end the class. That is for an unforced API system, x dot equals to ax, comma, for an unforced API system, x dot equals to ax, comma, the A matrix is Hurwitz. The A matrix is Hurwitz. Lyapunov direct stability theorem for API system specifically. Lyapunov stability theorem, and this is also the direct form for LTI systems. Please note that for LTI systems only, this result is both necessary and sufficient. That's why I wrote if and only if. But for nonlinear systems, Lyapunov stability criteria is a sufficient condition. Okay. Why does it have two versions? One is with respect to this inequality, and the same thing if you convert into an equality, then you will get the second one. That means here that PA plus A transpose B, suppose you are equating with minus Q, then as a whole it is negative definite, so that is you are converting it into equality for this ease and convenience for finding out the solution, because it is always difficult to find the solution of an inequality rather than finding the solution of an equality. Because for equality means simply that is you will have to solve a system of algebraic equations, right? But if it is an inequality, then you will have to apply the different kind of algorithm for solving an inequality. The concept remains the same. Only thing is that is one is the inequality version, other one is the equality version. Okay. So now if I read out, given an unclosed LTI system x dot equals to ax, the equilibrium point x star equals to 0 is asymptotically stable. In other words, we can say that A matrix is Hurwitz. The same thing. That's why I wrote or A is Hurwitz if and only if there exists a symmetry positive definite matrix P. This symbol means there exists a symmetry positive definite matrix P such that PA plus A transpose P negative definite. Okay. If it is equality format, then how would you write? If and only if for any positive definite Q matrix, if there exists a positive definite P matrix such that will be satisfied. Okay. So when Q comes into the picture, now the question is how would you test? You take any positive definite Q. Then if a positive definite P exists, that means the system is asymptotically stable. You don't have to take multiple Qs for testing. That is the advantage. And for that reason, this Q1 is very, very important. For any means that is like for you test for one candidate. If it is successful, you don't have to check for any other Q. Or at the same time, if it fails for one Q, then also you don't have to check for other Qs. But suppose instead of for any, if I would have written if and only if for a Q greater than 0, for any, if I would have written for A, then it's a dangerous thing. Why it's a dangerous thing? Suppose one Q fails, then it is your responsibility to find another better Q. If that too fails, then go for the third one, fourth one, so on. So although that is, it looks like a pretty negligible difference between for A and for A, but it is the difference is a big thing. Okay. So next day, second day, I will start the nonlinear version. Next day, I will write down the nonlinear stability theorem, and like gradually we will see the examples. Okay.
So for nonlinear system, you have the sufficient condition.
For LTI, it gives both necessary and sufficient. The proof is also there. If you see the slotted books or Khalid's book, the proof is also there. Okay, guys. Kashif, you move. I'm really sorry that it's very good. Sorry.